Yeah. Who's that? Recording in progress. Oh, okay, right. All right. So Cameron's going to give a talk this afternoon, Decrypting the Market, a network analysis of cryptocurrencies using vector autoregression. Cameron.
Correct. Thanks. Yeah. So here is my major review talk. Today we're going to be talking about financial networks and analyzing cryptocurrencies using vector autoregression. Title: Decrypting the Market. So let's start with some preliminary motivation. Why do we care? After all, this is the business of Wall Street. Who cares? Doesn't affect us. Oh wait, yes, it often does. We unfortunately get a lot of downstream effects from big macroeconomic events. So I'm sure many of you might remember things such as the 2008 subprime mortgage crisis. That was estimated to cost the international economy around $8 trillion. We also have some older ones, the 2001 dot-com tech bubble, which was estimated to cost around $1.75 trillion, as well as our favorite prolonged recessionary behavior following COVID-19 pandemic, which is estimated to cost at least $9 trillion. Quite a lot of money. Besides these big macroeconomic events, we also have kind of asset flash crashes or microeconomic events. We've had a lot of these in recent times, interestingly enough. So March this year, we saw that Silicon Valley Bank lost approximately 70% of its share price within 24 hours, about $20 billion. We also see a lot of this stuff happening in the cryptocurrency space, such as November last year, we saw the FTX cryptocurrency exchange collapse with $32 billion in valuation loss and $8 million of customer funds disappearing miraculously. A specific coin example is that May last year, Terra Luna lost 99.9% of the $66 billion valuation within 72 hours. So seeing these things, we might be interested in things like, does that spill over to other assets, or does that just die alone? So why do we care? Going back to it, we care because we are inside of these complex systems and we interact with them. The complexity often comes in the form of non-stationarity, so there's random shocks always changing these things, it's hard to understand them. And these changes can have very disastrous consequences for all of us. So a bit more technically, in this talk, we're going to be discussing markets from a complex networks perspective, and specifically investigating cryptocurrency. We'll discuss some things like what is a network, what is a financial network in this setting, and in particular, we're looking at essentially networks of influence. So how does one thing affect the behavior of another thing? We'll look at how do we build such a network, what type of methodology is used, and is it hard? Do we need to use some complex neural networks and all these fancy new things, or can you use some kind of simpler approaches to still construct a network? And is the result informative? So can we use some network analysis metrics to gain some insight into the kind of markets and economic behavior behind these things? And yeah, does this insight match what we assume based on economic intuition? We will also potentially look at is the network as $3 evaluations. This is a bit niche. We'll come back to this a bit later. But overall, some discussions of financial data in general, and specifically cryptocurrency data. There's a few things that make financial data a bit challenging in some ways. So, for instance, financial data is generally very non-stationary, which means the behavior changes over time. As we discussed before, these shocks mean that things tend to not stay the same. So let's say I took an example from last year or 2 years ago during COVID, and then I want to say what's happening in 3 years. Already those things are very disconnected. We also see that there's a lot of fat tail behavior. So we see a lot of big sudden changes in things often. So if you look at daily price changes, you might see that once in 3 years, there's just a humongous change that would not be expected. We also have that most markets operate at set hours and hence produce irregular time series. So this is things like overnight, most assets don't trade, over the weekend they don't trade, so you have these big jumps. So if you were stacking them side by side and you have Friday to Monday, that's suddenly a big jump and may imply there's more volatility than you would have thought. The benefit of cryptocurrency, however, is that they do trade 24/7 every day of the year, essentially, in online exchanges. So you do get a perfectly regular time series. You can always have a sample at each time. We also have some kind of overarching themes, such as the efficient market hypothesis, that says that in general, you should not be able to predict future returns, future prices based on past information, or at the very least, it's probably going to be hard to do so. Cryptocurrency, again, is helping us a bit in this aspect in that they are newer markets, and you could roughly hypothesize that they'd probably be a bit less efficient, and you might be able to find a bit more signal there. So what was the data we specifically looked at? we specifically looked at. So we tested many data vendors for historical data, trying to get some prices. This tended to have a few issues with it, as most of the things we tested had either like missing data or low coverage, or rate limitations when downloading it. That meant it would take like weeks and weeks and weeks to download. So it took a fair while, but we did end up getting one nice data set from cryptocompare.com. From this, we have hourly cryptocurrency prices for 2021 to 2022, which gives us 8,760 observations. And these observations are the price of a cryptocurrency in terms of the US dollar. So we tried to download the 750 largest capitalized coins. We got 280. Here, capitalization means like the total valuation of the thing. So the price per thing times the number of things. We cleaned out some things that essentially did not suit our analysis. Some things are designed not to change and called stable coins. Not go into too much detail, but we filtered out a few and we were left with 261 coins. And yeah, the market capitalization described there. Lewis suggested I give you some flavors of the coding fun that I had doing this. So yeah, you don't get it in nice CSV format. You have to use APIs to try and request JSON JSON data files. It's kind of complicated. You send off a request for an asset at a certain time and get back a bunch of JSON files that look like in the top right, and then it's kind of looks like strings, and you have to format it all and clean it. But also, there's just a whole heap of errors, or not errors, I guess, different ways of error handling in the system that made it quite hard. So, for instance, if I want to download Cameron coin, it doesn't exist, tells me it doesn't exist. If I want to download Bitcoin in like the 1970s or something, it just gives me back a thing with zeros everywhere. It doesn't tell me the error, it just gives me 0, 0, 0, 0. So there's a lot of different ways that it can go wrong, and it doesn't tell you which has occurred. So that was slightly challenging. But now that we have our price data, the standard thing to do in financial domains is to essentially look at returns. So we're looking at the growth per hour instead of the raw prices. So if something goes from $10,000 to $11,000, usually we more care that it's gone up by 10%, not just that there's a $1,000 change. This kind of makes it apples to apples comparison. And also people tend to take the log of that ratio. That's to do with some theories around geometric Brownian motion. Won't go into too much detail, but it is the standard thing to do. On the top, we have the cumulative returns of the top 5 largest cryptocurrencies over our time frame. So this is the total percentage return you would have had if you purchased it at the start of the year and held it. These are Bitcoin, Ethereum, Ripple, Binance Coin, and Solana. So we see that there's quite a wide dispersion here. Solana in particular is a bit hard to see there is the purple one, but we actually reached 4,000% return over the year. So that means it's gone up by around 40 times the price. So these things that look like they haven't changed. Yeah, the bottom one is just the log of this series. So this bottom plot essentially allows us to see that while in the top plot they don't look very related, they are kind of correlated in the way they're moving in the bottom once you transform them down a bit. But the difference in variances and scales makes it a bit hard to see. So now that we have a bunch of time series, we want to think about how we can construct a network. So within this network, each node represents an asset, one coin, and the edges or links, ij, indicate that there is a statistical dependency of the price series of speculative asset I and j. Specifically, we are generally working in a cross-correlation / causal modeling sense as we want to look at influence. This means it's a directed edge. This thing influences this thing. If we just wanted to look at are they correlated like symmetrically at the exact same point in time, that would create an undirected edge. We have a little diagram here to clarify this. So we're looking at the type of green edges here. So we have 3 time periods, 1, 2, and 3. We want to say like, is X influencing Y in the future, such as this edge here, or does Y influence itself in the future, this type of edge. This Y3 to X3 type thing is a simultaneous correlation. We do not count that here. That's more risk analysis. So specifically when people talk about methodology in this space, they usually mean the different ways of establishing the dependence between the two things. And in general, that is specifically broken down to be analyzing mean response effects. So does the value of X affect the expected value of Y in the future? Probably the most common way to do this I've seen in the research is to establish edge I. To establish edge ij, we consider the relationship between asset I and j. in isolation. So we get our 2 time series, and we throw away all the others and don't think about them at that point in time. We then do things like correlational analysis between lagged observations and current observations, or bivariate linear time series models, such as running like autoregression of 2 variables. There are also several transfer entropy-based approaches we've seen in literature that calculate more nonlinear interactions between the 2 series, and then kind of stores this based on transfer entropy. But regardless of the method you're using here to like create the links and estimate them, whether they're linear or nonlinear, there is a limitation in that if both I and J depend on some third series K, you may see I and J having spurious relationships, regardless of whether there is actually that direct relationship by not including the third variable. So our general approach to get around this is to consider multivariate time series analysis. So now when we look to establish an edge ij, we consider the relationship between I and j while conditioning on all the other variables that we have available to us. The specific way to do this is to use multivariate models to analyze the interdependent structure of the entire price histories kind of in one block. So that's multivariate. This provides less spurious relationships, as now we don't have those kind of triangular issues. However, one limitation is that it generally does require a larger number of parameters, as now we have to condition on a whole bunch of things. The exact model form that we looked at when doing this was vector autoregression. So this is a way of representing linear dependence between vectors of time series. Each observation is a linear function of the previous observations of all other assets. We have a form here where yt is equal to some constant plus a1 times 1 yt1. That means some linear matrix A times the vector of previous observations 1 time step ago, and then do this sequentially up to some specified time lag k, and then some error term. So VAR1, 1 here means that we have a max lag of 1, can be written as a general linear regression model, essentially a matrix regression, with the formula here. And you can also write higher order models, so any arbitrary k time lag in this type of form by stacking them. It makes it a bit harder to interpret, but just as you can do it. From here, there are many ways of estimating parameters AI, such as A1, but the GRLRM format supplies closed-form solutions in this kind of hat matrix that many of us might be familiar with from kind of univariate regression models. One benefit of this methodology also is that the number of parameters scales linearly n plus 1. We have a parameter for each of our other coins plus a constant. So how do we get a network from our VAR model? The gist is to, how do we get a network from our VAR model? Essentially, we construct an adjacency matrix to the network G by creating a binary indicator matrix. The element ij's indicates that our aij estimate here, what this means, is statistically significantly non-zero. So under some regularity assumptions such as finite variance, we can show asymptotic normality of aij in the central limit theorem. However, if you have fat-tailed error distributions, it does not converge to a Gaussian distribution. It converges to something else given by a theorem called the generalized central limit theorem. Essentially, fat tails converge to fat tails. Because of this, we actually run a bootstrap-based hypothesis test to find a null distribution for this estimate parameter, and then from there we can construct hypothesis tests. So now we have our network, we can plot it, have a look at it. So it's fun, everyone likes this. Here we have 2 different ways of plotting. We have a circular layout, and we also have a kind of standard Gephi type layout where the node size is given by market capitalization. This one on the right helps us visualize that, Bitcoin and a few of the big ones tend to be an astronomically large percentage of the total valuation of the industry. We might come back to these in a few seconds. For now, they're just rough visual aids. It's kind of hard to take too much away from them. So now that we have our network, we want to look at some network properties. A few standard things people look at is the degree of each node in the network. So the degree is the number of edges associated with a specific node. Because we have a directed graph, this has 2 forms. So we have the in degree of a node and out degree of a node. Out degree being the number of outgoing edges, and in degree vice versa. We'll also look at clustering, which is the network's propensity to form triangles. Essentially, you can find a node and I connect to this and this. What is the probability that they connect? How often do they those things connect. But for now, we have some plots that are a bit hard to see. It's blurry, but we have on the top the in degree and the out degree histograms. So for each node, we have an in degree and an out degree. We can make histograms from these. And then we can also plot the top 5 coins we previously looked at. We can label these in our histogram. So a few things we see is that the in degree tends to be relatively more condensed in terms of total, like the maximum we can achieve 261, so it connects everything else. However, here in the in degree, we see the highest in degree is actually around 16. It's not very high relative. And if you compare it to, say, the mean is 8, it seems to be around 2 times the mean. The out degree, on the other hand, is to show a much more substantial skew. We have values as high as 115 for certain coins, even though the median appears to be around 10. So that's 10 times larger than the median. So it's a much more skewed distribution. So something people tend to look into is the survival function or the complementary cumulative distribution function. This is essentially a way of analyzing kind of how heavy the tails of these distributions. In the in degree variant here, we see a very high curvature. That's kind of what you expect to see from a non-fat tail distribution, right? Rapidly decaying distribution. The out degree does have a much longer tail here. However, if it was what people commonly refer to as a power law or a power tail, it would look more like a straight line. So we see a bit of convexity here. So we roughly conclude that while it is highly skewed, it is not like a power tail distribution, which is often observed in different kinds of networks. We can also look at various correlation metrics and some statistics of our graph. In particular, on the top row, top table here, we have the seeming correlations of several things. So we have the in and out degree, the market capitalization of the in degree, the market capitalization of the out degree, the market capitalization of plus degree are all statistically significantly correlated with each other. So the rough takeaway from those things is that the higher market capitalized region has more connections. These connections tend to be with each other to the higher clustering. So yeah, it seems like there's a lot more activity going on in that kind of region of the graph. We also have some different node statistics that are unfortunately missing right now, but essentially that shows the average in degree and the out degree for the node. The network is 8.51, the average cluster is 0.096, and then the same values for our top 5 coins. Down the bottom, we have a few somewhat niche metrics. We have sortivity. Don't worry too much about those for now. If anyone's familiar with network science, they might be interested. But one thing we can look at is the number of connected components. That is 1. So essentially everything here is connected. You can't have disconnected node except for these like single disconnected node that attach to nothing. Besides that, everything else is fully connected with the network. We also have something called market cap sortability. Essentially means that higher market cap nodes tend to connect to other higher market cap nodes. So one rough interpretation of the statistics we're looking through is that it seems like a lot of the meaningful activity is happening within a small, high connectivity subset of the network. And we think, how do we test that if that's what we believe? So the main way we look at testing that is essentially with a reductive experiment, where we ask what happens to the network as we sequentially remove the most important elements of the network, most important nodes, and how does this change? Does the network become boring or structureless relatively quickly? So during each round I of this process, we remove the node with the highest out degree of the remaining nodes, and then we compare this reduced graph called GI here against the theoretical null graph given by an Erdof-Renyi graph. Essentially, that type of graph means we just get all the nodes and connect them at random, and it should produce something that's essentially low structure because it's purely random. From this, we then compare the degree distributions, our reduced node compared to random graphs with something called the tail divergence. Essentially, it's a measure of how similar to distributions. We won't go into maths too closely here. And we also want to track how our correlations change throughout this process. So we can plot the results here of the experiment. Essentially, the top picture here is to do the tail divergence as we move the nodes. So we see that it starts off very high. Our network very much does not look like a binary random network. And then as we remove the nodes, it comes down, and then it comes up again at the end. We also have the 95% bounds. So this is what we would expect 95% of the results to fall in if you had just run this process on a random network, so that it matched the one that we're comparing it to. We have done this for both the out degree and in degree. It's too hard to visualize the degree because the degree does start within those bounds. But both of them will come up towards the end because think that if we started with a random binomial network and then took out all the big things, it no longer looks like a binomial network kind of by definition. So the main takeaway there was looking at how long does it take to reach that kind of stage. On the bottom, we have a similar type of plot where we're tracking how quickly does the statistical significance correlations essentially go above the threshold, indicating that they're more statistically significant. We've done this for the in and out degree correlations, out degree versus market cap, and in degree versus market cap, and using 5% significant threshold plotted the red line. So we've seen roughly based on both these pictures by around the 50th node, most of the correlation is gone, and most of the deviation from a random graph also gone. So how do we interpret that? It seems to roughly align with our previous hypothesis that most of the network's information does seem to contain within a subset of a highly connected high influence subset of the network, which is around 50 nodes, which is around 20%. We measured this as a decline in the statistical deviation from a null network, the random graph, and scale divergence in degree distribution and decline in significance of correlations. Essentially, in conclusion, we will address some of the research questions we thought about earlier. So how do we build such a network? Is it hard? We roughly conclude that it was not that hard. We used a linear model and we found a non-trivially sized network. It was not just like one link in the entire network. Is the result informative and did it match our solution? The network structure was largely influenced by market capitalization alongside several outliers, which roughly matches economic intuition. And then we also have that most of the activity takes place in the top 20% of the influential coins, which also is a kind of commonly observed economic behavior. Where would we like to take this in the future? There is a couple of things we would like to do. We would like to look at non-mean response information. So that's like how does volatility flow into these networks, not just mean response. In finance, it's often observed that volatility has more statistically significant interactions than expectations. We'd also like to repeat the experiment with standard financial data and compare the results. You know, is it a denser network? Is it a less dense network? Trying to interpret that in terms of efficiency. And we would also like to perhaps look at recreating this experiment with nonlinear models and other machine methods. Here are some references. Here's a lovely photo of Elon Musk going to the moon with Ogden. The question? Yes.
So, go back to the slide that says ARJ is significantly competent. What do you mean by that?
This one?
Yeah, that one.
So that is a coefficient, like nonlinear regression, it might be 5 or 10 or something, estimating the relationship. We need to know, like, is that tiny, is that noise, is that significant? So do you know if you run a linear regression, like the stars indicating how significant the result is? It's essentially doing that in the matrix format. So for each one of these parameters, how likely is it that it would came from noise? So the hypothesis test essentially says, like, okay, assume they aren't related and it is noise. This is the rough distribution of what these things would look like. And then if you see the one we did fit to our actual networks, like way out here, it says a very low probability that that came from just random noise effects. That answers your question. Any other questions?
I'll find that interesting. What is it like? That's not what I did, so don't ask this question, right? But surely they're all so strongly correlated with Bitcoin. It makes sense to do a bivariate kind of analysis on even though coin and all the other coins, or is that like a bit doing a long way?
Can you clarify?
I wanted to do the bivariate with Bitcoin and all the others. Yeah, anyways,
With just conditioning on Bitcoin?
yeah.
Yeah, I mean, that's
To me, that's new.
the biggest one.
Certainly the one that's got a private space.
I'd say it's partially correct. So essentially, we're trying to condition on the entire market. First of all, that's what we're doing. And then you could maybe say you want to condition on like market averages. So you might condition on, say, the principal component of the entire matrix, which is, or like, let's say you could also condition on like the average return of all of them. So then if you wanted to do condition just on Bitcoin, it would be a question of, how close is Bitcoin to that first principal component? And like you suggest, it probably is pretty close. So like Bitcoin, if you were to choose a single node or a single point, indeed might be the strongest single covariance to include and to explain through power. Yeah, that because it's kind of designed to be the strongest one. So that's one of the things we looked at if we were going to do other conditioning methods. I actually had PCA conditioning in there earlier. I think I cut it out. But yeah, it is unlikely that one coin would be stronger than some like amalgamation of a few in a linear combination as you might get from PCA.
Oh, I had one more. If there's no one else. Could we just explain the in-degree, out-degree concept to me again quickly because I kind of missed that.
Yeah, okay, sorry. So imagine we have a degree, a node, and then it connects to 5 other things, 5 outgoing edges. That node has an out degree of 5, so it's 5 outgoing edges. If it has 4 edges coming in, has an in degree of 4, because it's 4 edges pointing towards the thing. So each node will have an out degree, number of outgoing arrows, and an in degree number of ingoing arrows. And then from that, that's for a specific node, we can generate all of them, and create distributions of the out degree and distributions of the thing.
I don't know what's happening at home.
Yeah.
Control.
What do we have? I don't think we have any questions.
All right, well, there's no further questions. Please join me. Thank you.